Now, what we'll do is we'll try to simulate this kind of a signal and see how through correlation we can get the frequency. We can estimate the frequency of a signal. Okay. So first, what we will do is, so in MATLAB, what we will do is we will generate a sine wave. It can be noisy also. Okay, and use autocorrelation and estimate the frequency, the fundamental frequency of the signal. If the signal is not corrupted, then we get the frequency of the signal directly. Okay. So here what we will do is we will create a noisy signal, apply autocorrelation, plot it, check the peak positions and compute the frequency. From the time period we will compute the frequency. So here the first step is create a signal. It can be noisy or it can be pure. First we will create a pure signal. Okay. So let us say t is equal to 0 in steps of 0.01. That is sampling period is 0.01 seconds, a 1 second duration. Let the signal be sine 2 pi f hertz t. So let f be dynamically specified. So input, enter the frequency. Okay, so we'll give this kind of a data, enter the frequency, this one. Yeah, now you can plot the signal, plot with respect to t, you plot the signal x, and you can give the title x label is time, y label is amplitude. Okay. Next. So next is get the autocorrelation. Autocorrelation built-in function is xcor. Xcor is cross correlation, that is between two different signals. Here xcor of x with x only. Okay, so we can specify like this. So how is this function used? We can see help on selection. So this is how we can use. So we can get the values and the time instants at that position. Okay. So here we had got the autocorrelation function to be a sinusoid kind of a thing. What is the amplitude and corresponding time instant? So time instants are the lags, amplitudes are the values. So we can get that. C are the values and lags is the time instants. So in that format we can get. Y is the amplitudes we get and lags, time lag, we can collect it. Now we will plot the autocorrelation function, that is y. Normally the representation is rxx. So you can just plot this function with respect to lags, comma rxx. So for this you can give again the x label is time and y label is autocorrelation. Okay, so we'll use the subplots. So first figure is subplot of 2 rows, first column, first figure, and the second one is second figure. So we'll see how it looks like. Now I'm taking a 5 Hz signal. So randomly I'm taking some 5 Hz signal. Now here comes the potential of autocorrelation, grid on. Okay, so our original signal was this 5 Hz component like this. In 1 second we have a 5 cycles, so we can easily tell it is 5 Hz. But if you take autocorrelation, what happens is, so at the 0 time lag, we have maximum autocorrelation component, that is magnitude. Now, when you shift this signal by half cycle, by half a cycle, like 0.1 seconds, then we get a most negative component. But when we shift the sine wave by 1 full cycle, then what we will be having is the positive components will be overlapping with the positive components and negative components will be overlapping with the negative components. So what I'll do is, I'll just copy this and try to explain this. So here, so in autocorrelation, what do we do? This is the result of autocorrelation. Okay. Now what I do is I'll just copy this. Okay, we cannot select like that, it's okay. Yeah. What I'll do is, I just want that sine wave. So in a new figure, I'll say I'll use this. So edit, copy figure, and here I'll paste it. Okay, so it looks like this. So when we have a zero shift, it will completely overlap like this. But when we shift it by half a cycle, it will overlap in this manner. Okay, so the position will be like this. When we shift it by half a cycle, okay, x of tau will be like this, x of t plus tau will be like this. So Here negative half cycle will overlap with the positive half cycle, and positive half cycle will overlap with the negative half cycle. Therefore, multiplication will all be negatives overall. At each point, the element by element multiplication will be negative, and integration of all the negative values will be the most negative value. Okay, so that is the idea. So in that way, what you get is, so when you shift by half a cycle, we get the most negative amplitude. Actually, if the signal was infinite duration, then we would have got positive peak and negative peak to be same amplitude. But now what happens is, now one half cycle is not overlapping on the beginning side, and one half cycle is not overlapping at the ending side. Therefore, we have less amount of overlapping. Now, when we shift it by one cycle, that is, one cycle is somewhere over here, yes, at this point. So if this is the amount of shift, if this is the amount of shift, now positive half cycle will exactly overlap with positive. So multiplication will give a positive value, and negative half cycle will overlap with negative amplitude. Again, you will get a exact positive. So in this way, you will get all positive values after multiplying the two signals. So integrating all the positive values will give you a positive value. So in the autocorrelation function, you are going to get a positive peak corresponding to the overlapping by shifting one cycle duration. Okay, so this peak is due to shifting of the signal by one cycle. Similarly, this peak is due to shifting of the signal by two cycles. Okay, and this corresponds to shifting of the signal by three cycles or three time periods. Therefore, if we can compute the distance or determine the distance between two peaks, that is the time period, and inverse of this time period gives you the frequency. Okay, so what we will do is, here this is time in lags basically. Okay, so we'll see. So first peak is somewhere over here, and the second peak is at 20, x is 20. So 20 shifts. So we have shifted 20. So 0 is one shift, 20 is other shift. So two positions we have got. So position 1 and position 2. Distance is 20 shifts. But 20 shifts by how much time? Time is 0.01 seconds. So one time period is this. It is something like 20 minus 0 into the TS, sampling interval. So we know that TS is equal to 0.01. In the code we have written like that. Okay, so time period is 0.2. We want inverse of time period, 1 by T is 5 minutes. So we can compute it directly like this. So frequency is equal to 1 by whole of this. Or TS, we can write it as, in the numerator we can write it as Fs. Okay, so TS is so much and Fs sampling frequency is 1 by TS. So we can compute like this. So this code we can put it in the code itself. So basically this is TS and Fs is equal to 1 by Ts. Actually, we specify fs and then we take ts. So fs will specify, let us say 100 samples per second we can specify. Then after that we can compute ts as ts is equal to 1 by fs. In this way also we can. So this line actually should be obtained by seeing the peaks. Okay. Now we'll experiment with another frequency. Okay. Let us now try for some 3 hertz and let us check whether we will get the same result. We'll enter a 3 hertz thing. Do we have 3 hertz? 1, 2, and 3 hertz. And we have got an autocorrelation function. We will try to extract the peaks. So first peak is at 0. Second peak is somewhere at 33. So 33. 33.27 is the highest and x position is 33. So now 33 minus 0 is 33 shifts is what we have got. So this is 33 minus 0 into, this is your fundamental frequency. Compute the fundamental frequency. We will get around 3.03 hertz. Okay, which is close to our estimation. Now, the magic is not here. Now let us see what happens if the signal is not so clean, basically. Okay, we'll create some noisy signal. Okay, noise is equal to some randomness. We'll introduce a randomness. Okay, of size of t. And let us see how this looks like. Plot noise. So it is only on the positive side. Okay. So what we'll do is we'll remove minus 0.5. Okay. So now we have a zero mean noise, that is the mean average of the noise is around 0. So this we will add to our signal. Okay. Our x noisy will be x plus noise. Now we will plot this x noisy. Okay, so now we will see what happens. X, we'll select everything and this we have to. So again, we'll choose some 5 hertz signal, enter. So in the time domain, the signal looks like this. It's quite noisy. We don't know whether, to compute the periodicity, where to where we have to see. It's not clear. So if we see from here to here, that's not exactly corresponding to 0.2 seconds. That is 5 hertz. But when you take autocorrelation of this, we can see smooth peaks. Okay, so see the peak to peak distance. One peak is here and another peak is somewhere over here. So 20 sample shift corresponds to peak distance. There is another peak. Any 2 peaks we can take. So there is another peak at 40. Therefore, 20 to 40 is one period, or 0 to 20 is another period, and so on. So 20 periods corresponds to 5 hertz. So this corresponds to 5 hertz. So we got a 5 hertz result. Let us increase the noise and check. So let us increase the noise by a factor of 2 times. Okay. So how will that signal look like? Again, 5 hertz component will see. So the signal looks like much more noisy. It is going beyond 1. It's coming less than 1. If you see a 0 to 0, you won't get exactly 0.2 seconds. It's quite noisy. But when you see the autocorrelation function, the autocorrelation function is very small, and if you can pick up the peaks, peak to peak distance, you will get the fundamental period. We will increase the noise further. For a 5 hertz signal, is the plot? Yeah, you can see here it has become much more noisy. It is very difficult to say whether it is 5 hertz or 3 hertz here, but if from the autocorrelation, the peaks can be easily picked, and the distance between 2 successive peaks can be calculated to be 20 shifts. 20 shifts, and that we can convert that shift amount or the lag amount to a periodicity. So Fs is this. That gives you 5 hertz. Let us, the last experiment will increase the noise much further beyond this. 5 times. Yeah, this is very noisy, and still autocorrelation is able to get us the peak to peak distance much more accurately than that we get in time domain signal. You can experiment with at up to what extent. If I say 10 times, if I give the noise, will it tolerate? Will autocorrelation tolerate? You can see here, what is the signal here? It is highly impossible to say it's a 5 hertz signal. What is the frequency of the signal hidden in this waveform? It's impossible to say that it is a 5 hertz. But once we take autocorrelation, we can easily estimate the distance between 2 peaks. Distance between 2 peaks is 20 shifts, and multiply that with a sampling period, and then we can take the inverse of this. We get a 5 hertz. So you can experiment the same thing with other frequency. Let us say I give some 7 hertz. Okay. So now it's no way you can say that it is a 7 hertz from here, but from the autocorrelation function, pick up the 2 nearest peaks. Okay, 2 successive peaks. Yeah, this is one peak, and this is 42.53. Yeah, these 2 are the peaks. So what is the difference between 14 and 29? So 15. Okay, so 15 shifts is the difference. So multiply 15 into TS and divide this to get the frequency. So this is around 6.66 or 6.7 hertz, which is close to our 7 hertz input frequency. So this is the application of autocorrelation. Okay, you can estimate the frequency of a very noisy signal with a hidden periodicity in it. Okay, we can extract that periodicity. So we can change this labeling. So here, so X label is lag. So 6 Hz signal. So compute, determine the shifts. So 17 to 33 is around 16. So 16. So Fs by 16 is 6.25 Hertz. So we gave around 6 Hertz. So we are getting around 6.25 Hertz. This is the application of autocorrelation, and this is how we can implement the autocorrelation and in MATLAB and verify the application of autocorrelation. One major application is we can estimate the pitch of individuals like us. Okay, each of us will have a unique pitch. Okay, so how do we do that? Means we take a very short segment of speech signal. We take a very short segment of speech signal. Okay, and that short segment, let us say of around 30 milliseconds of data we consider, and from that we can do the same process. So at what frequency that signal, the voice is recorded, we should know, that is sampling frequency, and the number of samples, that is a signal. So autocorrelate that short segment, we will get some waveform like this, and compute the peak to peak distance, and that gives you the time period, and take the inverse and estimate the pitch of the voice. So you can, if anybody is interested to go ahead with this estimating the pitch of your voice, there are many apps which can estimate the pitch. But if you want to estimate the pitch of your voice, like by coding here, we can do that. You can contact me personally. Thank you.